Hello everyone. We'll wait for one more minute and then we'll start. Let's begin. Today we will talk about time series modeling. I hope you all had fun doing your homework, and today we will move to the next topic. For those who don't know me, I'm Ivan Brigida. I worked for 10 years as a business intelligence analyst at Google. I have computer science and finance and data analytics degrees, and I founded pythoninvest.com website. And I'm also trying to use my analytical skills to invest into stocks. Here is an agenda for today. We will answer a couple of questions from Slido, and I'll show top comments from your home assignment responses. We will talk about system design view, step number 3. What is expected to see after this step, after we do all the modeling phase today. But before that, we will finish the remaining tasks from the previous stage. We will finalize creating a unified dataset. So we talked mostly about data generation and data joins. And today we will add to that set the new things, that is defining variable sets, working with the categorical data and generating dummies, performing correlation analysis and doing a temporal split that we will need for ML. And then when we have the data set ready to be used for machine learning, we will explore a few strategies, starting from hand rules or naive predictions, which will be very similar to what we saw in home assignments when we don't have any massive intelligence about which features needs to be used, but we select some or few features based on our experience and try to build a heuristic. Then we will switch to the statistical model called ARIMA. I won't go too far into this direction, but for those of you who studied statistics and econometrics, it will be a connecting point with all our machine learning models that will follow later. So you can use everything that you can do, and I highly encourage you to do that. And finally, we will talk about binary decision tree. So there are many other models that won't be covered in this lecture, and I'll list some of them so that if you want to go further and try more binary models, neural networks, or some of the more advanced models, you're free, feel free to do that. And we'll finish with recap. So today is model 3. Just to remind you, we started from module 1. We talked about different data sources and tried to join them and source as many relevant features as we can. Then we join that into one data frame or one flat table, flat file, depending on the infrastructure that you use. And I actually uploaded that file to Drive, so you can download it. You can mount your Drive to Colab and use it, or you can generate a new file with more variables, or even update that existing file every single day. And today we will try to produce a set of models, and the results of this model's execution will be a few more columns that we will add to the same data frame. You can, of course, separate those data frames and save all predictions in a separate table, but for the sake of simplicity, we will use one big table for everything. As usual, you can ask questions at slido.com using hashtag SMAZ. So let's start from some of the questions and comments that you had during the home assignment submissions, Slack conversations, and comments from home assignments. First, I'd like to compare first homework and second homework. It used to be 184 people who responded for the first homework, and we tried to create a simpler homework with less questions. And today there are only 95, or 95 is actually a very big number. Just 2 days ago, it was 50 of you who responded to the home assignment. So please don't stop trying. I will try to focus even more on less things, and I'll try to provide even more recommendations how you can solve home assignments more easily. But if you compare the median time spent on homework, it actually increased on 4 hours. So it used to be 4 hours, now it is 8 hours. And it used to be 2.5 to 6 hours, and now it is 5 to 12 hours. Hopefully, home assignment number 3 will be easier because it will be less technical, and you will be asked to slightly modify the code that I already have shared with you on GitHub. So what are the questions? Question number 2, is there a certain amount of points you need to get the certificate? There are no points or no threshold that you need to get. And not even home assignments are obligatory. So you can just submit a capstone project, but you're required to review 3 other capstone projects, so that the quality of projects is much higher for everyone. So if you submit a capstone project and review 3 other projects, you will get a certificate regardless of number of points that you got during home works. There were a bunch of questions about task number 2, number 3, number 4. And thank you. I learned that the data can change just in 1-2 days, and right answer can be completely different just after homework was shared. So I tried to check all your comments and fix typos and suggest solutions, and I will share first and second homework in Colab and do the presentation on YouTube to share my solutions. Question number 4. I'm running on my local computer and I didn't want to install TLEap, so I implemented CCI. Or some people had problems with implementing, with installing TLEap on Windows. So of course you are free to do whatever you want, and this can be challenging and interesting exercise to manually generate those features, so that you will understand the motivation, why they appeared, what are the thresholds when you want to buy or want to sell. But maybe you will still need to use some library to generate 100 features, because it may take you a lot of time to generate all of them manually. Question number 5, they were comments on all home assignment questions, to refine the task and to change the wording. And I can tell you even more that in question number 3, there were intersections in a list of stocks, so it's not fully correct, but you could solve it with different ways and you should have approximately the same answer. Selected comments. Comment number 1. Some of you mentioned that more and more skills are needed about stock market analysis and Pandas, and working with tables, data frames, data transformations. So please continue trying. Actually, I built new material on previous lectures, and I slightly extend the functionality and the approaches that we use, but sometimes I may use functions from lecture number 1 or 2 or 3. Comment number 2. Home tasks are very complex, not for beginners. Basic and advanced knowledge of stock market analysis and its implementation is very necessary. Yes, I agree that this course is not for beginners. So I wanted to combine everything, and I wanted to solve the end goal that you have end-to-end system that includes everything from data generation to modeling to simulation and to automation that can be used in real life conditions, so that you can build it for trading for yourself. And it turned out that it's quite a hard thing to do. So if we focus on real world tasks which are complex, we have to live with this complexity. Comment number 3, really great, good stuff so far. So some of you enjoy solving questions, and it's always great to hear. Please write more that you enjoy this or that question, or what do you want to see more, because it's hard to find something not that complicated, useful for you, and covering real aspects of investing. So I'm reading all comments that you share on Slack. Comment number 4, I'm finding a lot of problems trying to keep up with the content. Where should I find information to kind of put myself in line? I'm learning from Zoomcamp too. Is it a good idea? So my recommendation is to learn from everywhere. Just keep in mind that you have a limited time frame. You have deadlines. So just do whatever you need to do to solve the question, to understand this, and to move on. So you can do Googling questions or use Stack Overflow. Ask your experienced friends or experienced analysts. Ask ChatGPT. write down some gaps that you have and read about it in books later. And this is especially useful for the modeling phase that we will cover today, because ML models can be infinitely complex. Next comment. This model was much better. In the homework we could think about some strategies. This is a big plus. However, I did not get what it has to do with IPO and so on. So there was a suggestion that we can structure the course differently. We will ask from all of you the suggestions that you have after the course is finished. And the main ask from me is how to make it more simple and but still powerful, that is enough to cover many of the widely known models, ideas, strategies, features, etc. And I'll share here some of the answers for the exploratory question number 5. As I have said previously, there are no wrong answers here, and I would highlight that some of you offered to create additional features, binary, numerical, about the company, about the industry, about the product. This is a great idea. Then to use filters to evaluate performance in certain verticals to narrow down to one or few industries that are booming or growing now. And then maybe to go to the company financial indicators and feelings and define some thresholds or some conditions that on for example on net income greater than 0 or some other conditions based on your experience or based on the analysis from the public companies that were listed and were successful after IPO. Then some of you offered to look at the company's profit, at the volume of stocks, at the market demand and sentiment for the company, at the company's motive behind raising capital, or someone said that I want to buy shares and sell them on the same day, so it is a fixed one-day strategy, and I want to add specific sectors that are hot right now. Also, there were answers covering relative straight index or other technical indicators, but generally most of the answers were about industry trends, historical performance, financial ratios, sector/vertical, and generating new data to refine the approach and build some prediction model for the state of successfulness of an IPO. Okay, now let's move to the data that I prepared today. And first we'll start from final preparations of the unified dataset. Right now, because we have everything stored in one table and we don't separate it into different entities, it's quite important to understand which features needs to be included where. So that's why I created several lists of features. First list is called to predict. So it is everything about future. Is positive growth future 5-day? So it's 0 or 1. It can be 1 day forward, 30 days forward, 90 days forward prediction, and you can generate 10 of them, and then use your modeling phase and generate many models covering different features to predict and select some model and some strategy which works better. Probably our approach to generate predictions for 1 week ahead is not that strong, and we need to look at the 30 days ahead, 30 periods ahead prediction. Then there is a growth future 5 days. It's a numerical value for the exact growth, and it is useful not only for the regression or numerical prediction, but it's also useful to evaluate your strategy efficiency and profits from the strategy. Because if you have this model and you know when you predict growth and invest in that growth, and when you sell it in 5 days, you can have the final answer on the profitability of your model, just running a few vector commands in Pandas. Then the next category is to drop. It can be many features which you might leave in the data frame, like year, date, index underscore x, which is an artifact from some joint, quarter, even original open, high, low, close, volume feature. I don't use them all because they are absolute values, and this is not a very good thing to include absolute values to the model's predictions, unless it's a statistical model and they have some tricks like predicting not absolute value but predicting growth. One exception is that I do a transformation for a volume, and I include logarithm of volume just to have a smaller number which is distributed between 0 and 10 and not between 0 and 10 billion. Then there are a few features which we call categorical. Normally it's text features or some features that are derived from text. We will exclude them, but we will generate many additional binary features which are called dummies, and which are based on categorical variables. And next we have all numerical features, and this is the most important set of features that we have. Currently there are about 200 features in the dataset, or maybe with categorical dummies it is about 240 features in the dataset that are used for prediction. And as you can guess, it is much more powerful, or it should be much more powerful than just using one CCI index or one growth feature, or even 2-3 features that you might think about first of all. But of course, it's all needs to be checked. And these numerical features can be grouped into these subcategories. First, it's growth, everything that is related to growth, and that's our understanding about previous state of the stock, of other assets or benchmarks some periods ago. So we are saving information from the past, what happened 3 days ago, 5 days ago, 30 days ago, 90 days ago, in these features, and flatten the whole table. That one record, which is about 200 features and something that we want to predict, is actually a state of the world. So having this record, only this record, only one line, we should be able to predict some answer on the test data or on the latest data that will arrive just today. If you run the data today, so that you can use that for your investments. So next is technical indicators and patterns. It's many features and about 100 of them, and I think I used most of the features listed in TALib. There are many books written about it. If you see the technical indicators, especially for some assets like crypto, when you don't have many other fundamental factors, I think technical features are more important for that asset class. Macro, I included just a few macro indicators, maybe 10 of them. I have an article about 60 macro indicators. Again, if we see that these indicators are important, and we will see that later in this lecture, that brings us to idea that we might want to source more macro indicators or more local macro indicators for Indian markets or for European markets, because we have tickers from the US, Indian and European markets, but macro are all about the US markets. It can be custom numerical features, and I think that you still need to think about it and don't assume that everything is already covered, and just use your imagination, try to find some patterns, try to look into data and generate something that belongs to you. And many categorical dummies. For today's data set, we will generate dummies for months. For if it's January, February, so it's not year and months. If it's January 2020, because it's not a very useful feature. We just want to understand whether there is a spike on a specific month, on January, February, and we want to model that. So we generate one feature for each month, one feature for each weekday. Then ticker, we have 33 tickers, and I have a question mark because I'm not sure that we need to have these dummies. And you can check it. There is a trade-off. So if you add 33 features for each of the tickers, you will have more flexibility for models and more parameters. So you can model the individual effect of each stock. But the other idea is that your model can be too specific to a market. It can over-predict, and if you decide to use your model for the newly listed stock, which is not among those 33 tickers, you won't be able to do that because your model never saw that stock. So that's a question if you need to have it. But I included this in our current data set. Then next is a ticker type. It's an Indian stock, European stock, or US stock. I think it's different markets, and it's necessary to separate them. There are some key assumptions / considerations for the data, especially if you studied statistics and econometrics. Oftentimes people assume that observations are independent and identically distributed, which is certainly a simplification because we have a dependency between tickers, so it can be close on business companies, and between time. So two different records, yesterday and today and 1 week ago, may be very dependent, but we treat it as independent if you run statistical methods like linear regression. It's not that important if you go for a neural network or if you have many more features, many more parameters to estimate, but we need to think about potential assumptions and biases that we might have in the data. And also we assume that our data consists from the atomic data types. And what I mean by saying atomic, that is only numerical integers and float types, and nothing else. For example, why do I need to include 10 different features of growth 1 day ago, 5 days ago, or 10 days ago? Can I include just one array of 30 latest growth rates as one feature and create some model that will unpack this array or do some estimation with it? It's called nested features. There are models and approaches. We just do not cover it here. Or if you do some new modeling approaches like graph neural networks or LTCM or recurrent neural networks, you may need to have a different data organization, and this may be not enough. Okay, now let's create categorical variables. And before I go to the code snippet, I want to highlight that before having dummies, we had 184 numerical features, and all features they were of type float or integer, and the whole data frame, which consists about 182,000 records, it had 200 megabytes of memory. Then if we generate additional dummies, and that is approximately 60 dummies, 12 on months, 6 or 7 on weekdays, or 5 on weekdays, because trading is on 5 weekdays, and 33 for each of the stocks, and 3 for the ticker types. We will need to do some preparations if we want to use standard methods, which is called pt.get_dummies. So we will need to convert months and weekday and other features to string, so that that method could understand that there are a few cohorts of variables, so it can split it to 10 variables or 20 or 30 variables. Okay, let's look at the code snippet number 1. So everything is already shared with you. You can upload it to your local computer or open with the Colab and follow with me. So dummies, there are just 4 categorical variables, and I convert 2 of them to strings. Then I use one call pt.dummies and submits those categorical variables into that function, so that it produces many dummy features. And by default, it will produce boolean features, which is not ideal for us, because it's true or false. We want everything to be a numeric value. That's why I specified dtype equals to integer 32. And that's what you will see in the data frame. That's the original column name, month, and underscore April, August, December. So it will automatically understand what were the values for that feature and generate 12 additional columns with the zeros or ones from every single record. Same thing for weekday from 0 to 6, and same for tickers and ticker types. That's how we get dummy variables, and then we extend our numerical features with the dummy names. This is dummies list, and we also concatenate two data frames, original data frame with new data frame with dummies, just to have everything in one data frame. And that's how we have TF with dummies with 239 entries. Let's move on. Next thing is correlation analysis. That's some of you may say that it's not very insightful. It can change considerably in terms of features importance, depending on the model you use, but I still believe that it should be your first step in understanding data relations. For example, here we have two columns. I truncated these columns, and I showed only most negatively correlated and most positively correlated features. So as you can see from here, most negatively correlated features are macro DGS 10, it's 10 years T bond rates. This is GDP potential, year-over-year and quarter-on-quarter growth, brands growth, oil growth in 90 days. But the thing is that the absolute number is not very close to -1 or to +1. So it's actually quite close to 0. So you can guess that individually these features are not very powerful. That's a good and a bad sign. Good sign is that you need to create some really intelligent model or algorithm to combine those features in some way so that they can predict better together. And some bad thing is that I think that most of the easy ways are for trading and investing are not working well nowadays, and they could be beaten with statistical and machine learning models, and that's why we are doing all of that. From the most positively correlated features, you can see that the month October is positively correlated, and maybe in October everyone starts to invest more. It's close to the end of the year, and there is more activity and more growth happening. If this is a well-known fact, let's have it in a separate feature. And also growth BTC 7 and 30 days are included here. What is interesting that if you compare it with growth future 5 days, which is a correlation not with a variable that is that has only two values, 0 and 1, but with a continuous variable of growth. Growth can be 0.8, 0.9, or 1 or 1.1. So the numbers, the features are completely different, and the order of features is different. You can see here that two most correlated features are growth 3 days ago and 7 days ago, and here you see some technical indicators features and only one macro variable. But most positively correlated features are two more macro variables and one technical indicators. What I also want to highlight here that you should try to think about getting more features all the time. So maybe we are missing something. Maybe it is easy to get an additional macro factor or another data type, asset type, or some technical indicators. And I included one citation from econometrics courses. There is a term which called omitted variable bias. Actually, statisticians and econometricians, they researched this fact, and they said that if there is something relevant and important, and you don't include this to the set of features, you may have, or you almost definitely have, some bias in estimates and in confidence intervals, basically in the results of your model. But of course, it's not realistic to think that you know everything and you can source easily everything. So we live with some model of the world, and we have everything that we can get, but not more than that. Next idea, and this idea is quite familiar to many machine learning practitioners, is that you need to split your dataset into 3 subsets. And what is different in this exercise with time series data is that you can't use shuffle, you can't split randomly your data, because you will see data leakage. And because model, if you include something which happened just recently from your test data set, and you include in the trained data set, model will quickly learn this dependency, and it will try to find that pattern from the future to make predictions. So as you could guess, it leads to wrong predictions, and if you try to use that model for your out of sample, for your newest data, you won't receive good results. That's why I suggest you to use temporal split, and the idea is simple. You take 70-80% of the data, and here I mean same time cut for every single stock. From our 33 stocks data set, not all stocks were listed before 2000, and some of them are listed just 5 years ago, or 10 years ago, or 15 years ago. That's not the greatest sign for us, but still I suggest that we select some thresholds based on the overall time period. So I normally take minimum date and maximum date, and get 70-80% threshold between train and validation data, and add another 10-15% between validation and test data. So this is only NVIDIA stock graph, but you can do it for every single stock in your data frame, and you use all data available in training data set to train your model, whatever model you have. Then you use a few years from a validation set to find the best hyperparameters of a model. So even if a model is of a specific class, like a binary decision tree or a logistic regression or ARIMA, it has parameters or hyperparameters sometimes. For a neural network, these parameters can be number of hidden layers and number of neurons in each layer. And that's why you train each time a model on a trained data set, then you use validation data set to find the optimal hyperparameters combination, and then you come up with the best model that you have of that particular class and of specified hyperparameters, and use that model on a test data set, so that the model during the training and validation phase, it never saw that data, and you can pretend that you are submitting new data to the model. You see how it predicts, but you can compare with the future results because you know for this historical data set what happened in the future, and you can actually say what is a good model and what is not. One good idea to do finally with the data set is to check the distributions of the features that you want to predict, or distributions of the most important features that you found in the correlation analysis. And what you want to find there is that visual distributions for train, validation, and test sets are approximately the same. And the idea is that you train the model on some historical data to capture some patterns, but if there is some structural shift or markets are totally different, that's never happened before, or some pattern that was never seen before, or we have Bitcoin appear 10 years ago and previous trained data set didn't have it. The distribution of a test set and your latest data will be different, either on the things that you want to predict or on the features that you have as that you used to predict, and you try to balance them. You try to have them of a similar distribution. So maybe for us, if we see a big disbalance in the features, we will have not 25 years but 20 years or 10 years of data, and less data can be better for capturing new patterns, but it's worse to train models in a quality way. So there is always a trade-off. And for this chart, we see that left chart, train, validation, and test set, it's approximately distributed around 1, so that's growth in 5 days. Normally, it doesn't go far away from your previous value, and that's a value 1, but it looks like a bell curve, bell-shaped distribution, and visually it is similar. It just train data set has more data than validation and test data set. And on the next slide, we can actually compare more precisely these distributions. And on the right hand side chart, we check the distribution of is positive growth 5 day, and here for NVIDIA there is some distribution problem. For a training data set, it was 46% of cases when the stock was not growing, and 53.7 cases when the stock was growing, just first 20 years of the data. But then in the validation set, which is probably between 2015 and 2020, the number of points when the stock was growing increased to 63%. So it is some difference. What is good that now it's lower, so it's 56%. It's closer to the trained data set, and I don't see a big problem here. And actually, if you include more observations for other stocks, this distribution will be different. And here I also included one additional way of comparing graph distributions, especially if you are running a regression and you want to predict not the binary variable 0 or 1, but you want to predict a specific growth or decline, whether it was 5%, 10%, or minus 5%. And you are actually very cautious about these distributions, because if a test set never saw the growth lower than 0.6 or higher than 1.4, actually it's a test set. The train set was much wider, but it can be a reverse picture as well. So that train data set never saw the cases when stock was growing quickly, and it will never predict at the test set that the high growth numbers. And one additional thing that you may want to do here is to compare these bar plots. So this is 25, 50, and 75% quantiles just visually presented at the graph. If you look visually, and the distributions look very similar. They are all bell-shaped. They are all of same width and of same shape, but there are different number of outliers, and you can see it from these numbers and from maximum and minimum stats here. So you might have an idea that maybe you want to remove 1-2% of outliers completely, and your estimation for regression will be more robust. But it may not predict exact numbers for a big growth or decline dates, which you're fine with. It's hard to predict, but on all other cases it will be more robust. So that's the idea. Now let's start doing some modeling exercises. And first we will talk about hand prediction rules. That's a very similar idea with what we had previously in homeworks, simple strategies. Next it will be ARIMA statistical model, and finally it will be one binary model, decision tree. I won't cover today logistic regression, which is another binary model, or ordinary regression, which is a numeric model, random forest, neural network, or even ensemble learning. But I will prepare you if you have this data filled in the data frame. It's quite easy to expand that data frame with slightly more predictions and combine those predictions together, which is called ensemble learning approach, to create an even better prediction. So first, and probably the most important conceptual slides today, if we think about manual predictions or naive predictions or heuristics, how we can generate those predictions to the data frame. And we will look at code snippet number 3 in a few minutes, but before that I'll explain you what are we going to do here. First, we have a big data frame that has everything. Numerical features, categorical features, some other artifacts, and we will add one column for each new prediction. And these columns will have the same prefix. It will start from pred, and pred 0, pred 1, pred 2, and we will add some details about the type of the prediction. First, pred 0 manual CCI. Same idea that we had CCI more than 200. How we predict this, we do one line of code and we add this prediction to the data frame. Then I want to add one thing that you want to keep in mind is how many features did you use for the prediction. This is the first thing. And second thing, whether you used any parameters to estimate your best decision rule. So here we use a fixed decisions rules. So it's all CCI more than 200 or growth more than 0. But maybe CCI should be more than 300 and growth should be more than 0.5. So that's what I call parameters, and that's what you may need to study to improve your prediction rule. But when you're done with these predictions, you will have 3 prediction columns. So prediction 0 is CCI more than 200. We saw this. It's a rare event, not many times it happens, and most of the times it will predict 0. Then another prediction growth one day is more than 0. Actually, it should be more than 1 here, because we have a distribution of growth around 1. I'll check in the code that it's not a mistake. The idea is that we just look at the latest available 1 period growth. So growth adjusted close today versus adjusted close yesterday. And if it was growing today, then it will be growing for the next 5 days, which is a simplification, of course. Next idea is that you may add some additional conditions, and you may need to use more features here. Let's assume that you include growth 1 day is more than 1, and growth of benchmark S&P is more than 1. So here it's more than 0%. What I meant here, and that's how you produce this prediction number 1 and prediction number 2. I included all original values that are used for the prediction, CCI growth 1 day and growth S&P 500 to the data frame. And I can see here that the code is probably correct, because prediction 1 on growth 1 day is 0 when growth 1 day is less than 1, and 1 when growth 1 day is more than 1. So the code is correct. And we have several predictions here, and then we have a real value that we want to compare with. And here actually we care only about positive predictions. It is another simplification that it's much easier to do long strategy or invest in growth. So we want to predict growth, and we look only at the positive predictions when predictions are equals to 1. And here we have 1 observation when predictions were 1, but actual growth was negative. And this is called false positive. So that's we predict it to be positive, but it's false. And then another line, actually both predictions, they predicted 1, and that it will be a positive growth, and this positive growth happened. What you can think about here is that prediction 1 and prediction 2, they are very similar, and prediction 2 is actually more strict. So it says that I want to focus only on those days where my growth was positive for the ticker, but also the growth of overall market was positive. So it will predict 1 on the same predictions for prediction 1, but sometimes it will predict 0 when growth for the market was negative. So it can be good, it can be a bad sign, we don't know. And next thing is that we want to evaluate somehow the quality of the predictions. And if we work with the binary predictions and we want to have predictions whether the stock will grow, that is 1, or whether it is not, it won't grow, it is 0, we can calculate the metric which is called precision. And this is unusual for binary models. Often when you do some educational binary predictions, those models are selected by looking at the accuracy metric, which treats not only correct predictions, but also not only correctly predictive positive predictions, but also correctly predicted negative predictions. Here we say, let us have less predictions, but we want it to be more precise. That's why we divide true positives on true positives plus false positives on all predictions that we predicted to be positive. And for the first case, you can see that there were only maybe about 800 positive predictions, and 450 of them were truly positive and 344 were negative. So it's about 56.9% were positive. It's not much more than 50%. So here in time series predictions for finance stats, you won't expect 70, 80 or 90% precision or accuracy, as you can see sometimes in many other problems. These numbers are already a good start. Whether it is a good enough thing for us, whether it can drive us to earn some money and to have a profitable strategy, we don't know yet. We will know on the next lecture. So the next prediction is manual prediction just on growth one day ago. And this time it predicts 14 or 15,000 times positive positive growth predictions out of 30k test data points, approximately 50% times. And the precision is quite close. Still, every single percent may be very important for the profitability of your strategy, and we will try to leave those models which have higher precision. So this one is 0.55, and the next one, the strict prediction about growth one day and S&P growth one day, it has less data, 10k data predicted, but the prediction accuracy. So our rule is probably not working for us in terms of it's not increasing the precision. We will have only 54.7% of accurate or correct positive predictions. There are a few things to think about if you do these manual predictions. First thing, what is the best model? And here the first candidate is CCI model, but you never know, because it happens not very often. Only 800 predictions over the last four years. I think test data 15% out of 25 years. It's just last 4 years. And if you calculate the money that you can earn with these few trades, it can be less or it can be more than the other model. The main idea is that yes, we are selecting models by some metric, by some machine learning metric, precision, accuracy, or root mean square error, or anything else. But this is not the end rule for us and the end result, and we need to come with something more complicated. So it's not enough to have only one quality metric. Next next idea is, why don't we introduce some parameter to estimate our to improve our rules. For example, we can have a rule CCI more than x, and we can select this value of x between 200 and 400 and find some precise value of 250 or 300, exactly in the same way that we were trying to do in the homework with the number of days to invest after IPO. Here we introduce some degree of freedom. We introduce a parameter, and if you worked with machine learning models, it's exactly a decision tree with one node if you have only one feature CCI. So that's what we have here. Another idea, why do we have growth 1, 3, 5, 7, 30 and 90? Maybe we need to include growth 45 days or 15 days. So you need to experiment. Usually markets don't have that long memory, but it depends if you want to predict growth for 1 day, 1 week or 1 year. The memory for these predictions will be completely different. Now we also need to think about what strategies of trading we might have. Do we want to invest only in growth, in a long position that we predict that something will grow, we buy it now and sell later and it grows? Or we can actually trade on short positions when we predict that it will go down and we can make money from that trend. And last but not least is you also want to think about the distribution of positive predictions. Let's assume that we had some period of growth. And this period actually happened just recently in 2020, 2021, just after or during COVID. And our models can show very happily that we predict a lot of growth, but these predictions are concentrated only on that period. That means that yes, you could trade there when everything was growing, but what about now? If you have a market that is not moving anywhere, you still want to have some ideas where to invest. And now, okay, I forgot to switch to the code snippet number 3, because this is an important snippet. I think correlation analysis code snippet number 2 is just 2 lines of code. It's quite simple. You can read it by yourself. Now code snippet number 3, and it's combined with okay, it seems to be a wrong numbers here. It should be okay. I have 2 code snippet number 3 in Colab. Here are manual hand rule predictions. First, why does it work? If you if you have this expression u underscore df dot cci, it will return you a series of values. And if you have some simple expression like more than 200, it will do value after a value comparison with 200, and it will generate a column or a vector of true and false values. So that's why it works when you define these new columns using these vector operations. So this is prediction number 0. We generate this column of true and false numbers, and we convert these string values or boolean values to integer, so that false is 0 and 1 is true. Same idea is for new df.growth, 1 day is more than 1, and same idea with and with combining two conditions, so that we want to have first condition to be true and second condition to be true in order to have the resulting condition to be true, and we convert it to 0 and 1. That's how we generate these predictions. And next thing, I define a new feature set which is called predictions, and I have everything that we ever have during our work here. I'll have it in a prediction feature set. So for now it is just 3 predictions, and I also generate a column which tells me whether the prediction is correct or not. So I look into all columns that I have for now or later. So the function is exactly the same, and I compare the prediction. We just need to know whether it's a binary prediction or numerical prediction, so whether you compare with the positive growth 5 days, which is a binary variable, or with the growth future growth 5 days, which is a numerical variable. For now it's simple. We have only binary predictions, and we compare prediction with actual value, and that's how we have 1 if it's true, if it's a true positive, if it's a right prediction, and 0 if it's a wrong prediction, if it's a false positive or false negative. And that's how I calculated these numbers on the precision. When I have these columns generated is underscore correct prediction 0 or is underscore correct underscore prediction 1 or prediction 2, you can quickly see the quality of the matrix just with one loop. We have just a few more slides, but they are becoming more complicated. I won't spend much time on this, and I won't go into the details of code snippet number 4. What I wanted to highlight here, that if you studied statistics or econometrics, it's a great knowledge, and please try to use it. Please try to have it in your predictions and to compare versus hand rules and versus well-known machine learning predictions like a neural network. What happens here is that we have 20 years of data history, and the idea of a ARIMA model or Autoregressive Integrated Moving Average model is that it doesn't look at any features. It looks only at the previous values of time series, and here values are adjusted close price. So we have a train plus validation data set for 20 years, and this is a green line. I just truncated it, and then at some point we found the best combination or best hyperparameters for this model, P, Q, and R. And I know that P equals to 6, it actually means that this model will look only at 6 previous values of the time series, and it will try to estimate a perfect perfect parameters or ideal parameters that minimize the error, the prediction error for that time series at that moment of time. That's why we try we start to predict on the first day of test data, and that's why you have some gap. It's because I predict on 1 period ahead, 2 periods, 3, 4, and 5 periods. We want to know whether future stock price will be positive or negative, and future in this context, because our variable that we compare with is called future growth 5 days. We need to make five predictions. And for this statistical model, it's not very good, because further you go away from the current prediction. And here I have red real stock and blue predicted stock, which seems to be very close. But if you think about small fluctuations of growing up or down, like 1, 2, 3, 5%, even these visually close graphs can provide very different accuracy. What else did they found? That this method it's very slow, and I ran only 500 out of 900 points for one stock, not all 33 stocks, and it took me almost 1.5 hours. And it's produced suspiciously high precision of 88%. So if any of you did this before, probably I made a mistake somewhere. Please let me know where the mistake is. But the general sentiment about this model, and when it is usually used, still widely used, is when you have some generic time series like interest rates, or you have a financial planning of sales, something that you don't know what are the factors that actually influence this or that variable, and you want to build a short-term generic model. For us, it may be enough. If we try to predict five days ahead, and we are fine with retraining the model every single day, and that's why it is slow. So retrain for this model, it takes only 10 seconds, but if you go into neural network, retrain can be 1 hour or 1 day, depending on the size of the network and size of the data. So you can't afford it for bigger models. But my point is that yes, these classic statistical models and hand rules and ML models, they should all compete with each other, and you should select the best from it, and ideally try all of that. And now what we have here, this is a binary model of decision, which is called a decision tree. And this is why we built this big data set, which consists of 200 features. Previously, in all our hand rules and manual predictions and ARIMA model, we didn't use most of the features. This time, we are starting to use all of them. And the idea with a decision for a decision tree is quite similar to what we had. You can read about in the textbooks, but let's assume that we don't know what features are the best. We know that there are 200 features, and just some of them are correlated more or less but which features needs to be selected, we don't know. And let's ask model to define these features. And the model will try to have a series of simple rules or experiments to make a final decision about investment. So we still have, as an input for that model, we have one record with 200 numerical features and one feature that we want to predict. Let's assume that we fixed a hyperparameter for that model. It can be 10 or 15 or 5 or 20, and it's up to you to select. And actually, it will be your home assignment to find a better tree model. And for this experiment, we have a tree with 10 layers. That means that this tree won't have more than 10 features used. We used previously for hand rules 1 feature or 2 features. This time we will have 10 features, and not just 10 features that we know, but 10 features that make overall predictions accurate enough or optimal in some way. So you can read how decision trees are working and estimate it. But here is the result, and there is a visualization that if we have some record that we want to predict, and the decision tree actually says to us that look first at the GDP potential US year-over-year growth, and if it is less than 2.7, go to the left subtree, and if it is more than 2.7, go to the right subtree. It's quite natural because there are two macro regimes of growth for the US economy. If it's less than 2.5 or 3%, it's close to recession. If it's more than 2.5%, it's close to growth. So it actually confirms well-known economic facts, and this is a good sign that you can explain. And that's another thing, that you should try to explain things that you see, and don't treat any model as a black box. And this is extremely important for financial time series. Then we checked the first feature and moved to the left to the right subtree. Dependent on the subtree that we are in, on the left subtree it will check FAST-D feature if it's a technical indicator. If it's less than 0.25, again it's already showing some optimal parameter. You might not know about it. If you are in the right subtree, it will look at the oil growth in the last 30 days. If it's less than 0.5% of growth, then you go into the left subtree. If it's more than 0.5% growth, you go to the right subtree. I don't remember actually what is a FAST-D technical indicator, but for the oil growth, again, it can be explained perfectly. Oil is another big asset for investments, and if oil is growing, maybe traders, investors can switch their demand to commodities, to oil, to these types of assets. So that's why it tries to separate with the condition, and separate in such a way that the division between left subtree and right subtree is more pure. So again, you can read about the purity or Gini coefficient, but that's how it selects the optimal parameter for estimation. At the level number 4, we have 4 different options, and we have growth of Brent oil, of gold, of Dow Jones index, and month September. We used to have month October in the correlated features, in the most correlated features, but for this particular model, which treats all features together, we have month September as an important parameter. So if you think about this model, it is linear on parameters, so you can think about like simple model. If there is a nonlinear combination or dependency, it won't predict perfectly, but it will predict something. And parameters that are estimated when you fix number of levels, it's more than 1-2 parameters, but it's less than thousands of parameters. In order to do this exercise, I actually had to do 2 more steps on data cleaning, because I generated variable logarithm of volume. It equals to -infinity when volume is 0, and I had to find all those cases when it is -infinity or +infinity and replace that with 0. And another thing which was not visible straight away in the data set, that I need to do something with missing values, with nulls. And first thing to do, and first normally analysts they just try to drop that data, but we have features of Bitcoin growth included, and that means that we can drop half of the data before 2010 just because one feature is not defined. So I replaced all those features with zeros, even if it has some coefficient estimated. If you multiply that coefficient on 0, it normally means to 0. It equals to 0. That's it's a different strategy for non-replacement, but I still have the same number of observations. I don't lose the data, and this is a good sign. So we talked about visual representation, and one more slide and we'll check the code. One thing which is oftentimes forgotten when we talk about machine learning models is explainability. And explainability is very developed for statistical models with confidence intervals, with goodness of fit for the models, with many other things or methods to look at. You can find some explainability in most other models as well. For example, if it is a linear regression or a neural network, you can calculate gradients, or there is a model called Shapley, or in this case, actually the model from the library scikit-learn, the decision tree, it already provides you with the features importance. And you can see here that first, if you compare with our previous hand rules, the precision is slightly better. It is 56.5 and 57% versus 54, 55 and 56%. So this is a good sign that we used more features and we used in a smart way, that we are not overfitting, we have a better model. But these models are quite close to each other, but the features importance is somewhat different. The first model, which has only 10 layers, it is like a macro model. It doesn't look at the historical growth of a stock or technical indicators of a stock. It says, I can predict relatively well just by looking at the macro conditions, at the inflation growth, Dow Jones, interest rates, gold, oil growth, S&P, and GDP growth. And the right model with slightly higher precision, it says that no, actually, let's look not only at the macro parameters at gold growth, oil growth with different time periods, the 365 days versus 30 days. But also let's check technical indicators, Netter, OBV, AD, and tricks, and previous growth in 90 days. It's slightly surprising that growth 1, 2, 3, 5, 7 days ago is not among the most important features, but this is another way of understanding of the whole market. So now we know that maybe we want to include more macro variables. Maybe we want to look into other factors that influence oil, gold, or like maybe we want to include silver here. So that brings us to the idea of how we can source more data. And if we check the code, we are slightly over time, and it will be a brief explanation for the last piece of code. Okay, it's a few lines of code. First, I have features lists. I know what I want to predict. I generate train data frame, or actually it's a train and validation data frame, and you will be asked to split it back into train and validation and find the best hyperparameters for a model tree, and a test data frame. And then I have only features data frames x underscore train and x underscore test, wide known abbreviations, so we use exactly the same ones. I do the replacements of infinite values and fill none, so that we don't have any problems with the data. I have here remove outliers, but I decided that I won't go for a binary prediction for removing outliers. It's more for regression models. And when I have x train and x test and y train and y test, it's what should we see in train and test stats. I do the estimation, use scikit-learn library, one line of code. I specify maximum depth, which is a hyperparameter. It can be 5, 10, or 20, and it works relatively quickly, 1 minute, but it's longer than 10 seconds, and you can't do these estimations for 30,000 of observations. So we need to estimate to find some model, fix that model, and use for all predictions in the nearest future, and maybe re-estimate periodically, once in a month, once in a quarter. And that's why we split this. So we have inference in a decision tree. We already have a classifier, and we provide some data frame and true values that we want to see. And that showed to me the accuracy and precision 57% for a 20 levels tree, and 56.5% for 10 levels tree. Okay, so just to recap what we've learned today. We finalized a unified data set. We did a bit of data transformations. We defined feature sets. We generated more dummies. We created a temporal split, which is a specific column in our data frame, and it says whether this observation belongs to a trained data set, validation, or a test data set. We talked about binary hand rules or naive predictions. Then we briefly looked at the statistical model ARIMA. There are many more statistical time series models, and we discussed decision trees. Out of scope for today, random forest, logistic regression, ordinary regression, and neural network. So first three, they are very easy to adjust to what we see here, maybe 1, 2, 3 lines of code. You can read about it in scikit-learn, perfect library. Feel free to try it. Neural network is slightly more complicated. You can do it in TensorFlow, for example. You can have many more parameters, and you can have a nonlinear estimation. That means that the model is more complex and it has more degrees of freedom. If it is properly trained, this neural network can cover all previous examples that we had. So that's why you might want to have it in your project. Maybe just a simple neural network included to compare against all other models. As for homework, I already have some ideas what I want to include, and these ideas are found in the code with to-dos. I will finish it in 1-2 days. As usual, it will be probably 4 questions and 1 extra question for exploration. The deadline will be approximately 1.5 weeks after the homework is announced. And please ask more questions. Please share about this course. And thank you for listening, and see you next time.